Hello, Stats class. Here's lesson 11.1a, the beginning of a new unit. And in this unit, we will be working with categorical data again. And you might be thinking, hey, we've done categorical data before when we did proportions, right? So proportion tests, that's kind of like this, except what we're going to do in this chapter is allow it to have many categories instead of just two categories. So for proportion tests, we have successes and failures and nothing else. Now we're doing many categories. So we're going to compare the distribution of our population, which we're going to use a sample to estimate that, of course, and we're going to compare it to a hypothetical distribution that we think is true. And that would be the proportions for all the different categories. Hypothetical. I had to stop and think about how to spell that. So in the warm-up, they walked you through how to write hypotheses and how to do the calculations. They basically did everything except the plan stage, and we're going to put that off until next week. But from the warm-up, I hope you didn't skip it because it was good. We learned how to do step 1, which was the hypotheses. And they are usually written in words in this unit, and that's different. I'll show you why. So what we did in the warm-up, I'm just going to repeat a little bit of it here, but I still hope you didn't skip the warm-up, right? So our null hypothesis was that the proportions of admitted students were the same as the proportions of each race in applicants. Applicants to Harvard. So proportions of admitted students at Harvard are the same as applicants with regard to race. Another way of saying that, we said in the warm-up, was they didn't discriminate against some races and didn't favor others. So you could say it several different ways, but the idea of these proportions being the same is the important idea in the null hypothesis. It's always going to be that the proportions are the same as what we think they are or what's claimed. And then the alternate is always that something is different. It doesn't have to be all of them. It just has to be at least one of them. And in this case, the Asian Americans were saying that they were discriminated against, but really any difference from what was advertised would be would help their case. So they're not going to try and prove specifically Asians. They're just going to try and prove in general something's different. So I want to say this is what the normal way is that you would write it, but I want to talk about, or you could write it in symbols. Not very common to do it this way, but you could. And the reason I don't prefer it in symbols is I think it's harder actually in symbols in this unit, because if you want to do symbols, you have to do all of the proportions in your null hypothesis. And so I'm going to actually look them up because I want to make sure I've got it right. Oh, hang on, I don't actually have it right. So let me just get that. So you would have to say the proportion of Asian students is 0.575, and the proportion of Hispanic students is, I think it was 0.031, and the proportion of Black, you'd have to write that down. This one was 0.008, I think, and the proportion of White, and it kind of gets tedious after a while. What if you have more than 4 categories? That would be terrible. Is whatever's left, but I have to remember what that was. So I'm going to really quick calculate this because I want to know. It was 0.5255. Oh gosh, I've got the wrong proportions now. I don't remember what it was, I confess. So it was whatever's left after those other 3 I'm going to calculate it because I really want to know. Pardon me for a minute while I calculate something that I should have had written down in advance. Pretty sure I'm right about those three. So 0.386. So that's kind of a lot. And if you had more categories, you have to write them all out if you're doing proportions. So imagine if you had 6 categories or 8 categories or something like that, where you just have to keep writing all these different proportions. It's easier to say, is the same as the table given above, or something like that, which is what often happens with the words version. And so, feel free to be lazy on that. The alternate would be that the probability of Asian is not 0.575, but it might not be Asian that's off. It might be something else. So you'd have to write, or the probability of Hispanic is not 0.031. And you'd have to keep writing all of them, right? I personally wouldn't do that, but I'm going to do it once, just for you. And then I'm going to stop doing it and always write it in words after that. So this is getting at that idea of at least one proportion is different. I don't know which one of these is wrong, and maybe more than one is wrong, but that's my alternate hypothesis. I think this is easier. This is kind of cumbersome, and I don't like it, so I usually don't do it, except to show you, because some people really, really, really want to write those symbols. I did an example last year where it was M&M colors, and there were 6 of them, 6 different colors, and so we had to say proportion of blue is this, and proportion of orange is this. Oh gosh, that takes forever. Just don't even do it. This is the same as saying at least one is different. So that's what we're usually going to do. So then after step 1, which is the hypotheses, we're going to come back to that step and do some more. You would normally do step 2. We are skipping the plan for now, the plan stage. We will come back to this next week because I don't want to put too much in this first set of notes. So you don't have to worry about planning yet. We will eventually, probably Monday, talk about planning. The warm-up walked you through how to do the calculations. And so we have this new chi-square thing that's a fancy x squared. It's the Greek letter chi. And I have a corny joke about that I'll tell you in a minute. It's pronounced chi. It's not pronounced chi. Here's my corny joke. It's not pronounced chi because if it was a chi-square test, it would be a t-test. Get it? Chi-t? Oh, yeah. Yeah, that's a great joke, isn't it? So chi-squared is our new test statistic. And it's found by calculating observed counts compared to expected counts. And so what you do is you do observed is the counts in each category of the sample. And notice that's counts and not percents, not proportions, not percents. It's definitely counts. And I gave you the counts in the warm-up, so there you go. Expected values you calculate based on your table of hypothetical percents. So you take your hypothetical percents, which are generally given to you, and they're the same as what's in the null hypothesis, and you multiply them by the sample size. So these are from the null hypothesis. And so basically your first expected count is your sample size times your first proportion. And then your second expected count is your sample size, that's an n, sorry, sample size. I started writing an equals and an n at the same time. It doesn't work. So sample size times your second proportion, and you keep doing that for all the proportions. You actually did that in the warm-up, and hopefully it made sense to you at the time. etc. You do that for each category. And then you combine these to calculate chi-squared. So you use these to find our test statistic chi-squared, and it is officially the observed counts minus the expected counts. You do that for each category, you square it, you divide by the expected counts. The table in the warm-up walked you through all these steps, and I hope it made sense. And then you add them up. This thing means sum. Find the sum of this calculation for all the categories. So you add it all up. We did that already in the warm-up. I want to show you how to make the calculator do it maybe a little bit faster than what you did in the warm-up. So there's a little bit of a shortcut on the calculator. Not as good as our other shortcuts, but I'll tell you about it just to be sure. For the calculator thing, you put the observed counts in list 1, and you put the expected counts in list 2. And I think I just ruined my list 1 a minute ago. I'm going to go see if I messed it up completely. No, I didn't. Okay, good. So what you do, actually, this is the whole table from the warm-up. So the list 1 is observed, list 2 is expected, should be the same numbers you just saw. List 3 is the subtraction, list 4 is the squaring them all, and then we divided them all. These are the same numbers you got. You can go straight to list 5 much quicker than what we did in the warm-up, and I wanted to show you that. So I'm going to delete list 3 or clear it out and show you how to do it much faster. So the shortcut is you take list 3 and you tell it to do this formula. You tell it to do list 1 minus list 2 squared over list 2. Here's how you make the calculator do that. So you go over to the list 3, go to the very top of list 3, because if you're up here, you can enter a formula. And then the formula is going to show up down here when I type it, but I'm going to do parentheses, second 1 to get list 1, minus list 2, parentheses squared, divided by list 2. And that is the fast way to get that last column of the table is what you need. Much faster than what you did in the warm-up. So now that you've done it the long way once, you can do it this way forever after. These are the same numbers you should have had in the last table of your warm-up. And then what you do is you add them up. Or there's a faster way to add them up. So chi-squared is supposed to be the sum of all of that. And what you want is the sum of list 3. So this little shortcut here is much better than what we did in the warm-up. So to get the sum of list 3, there's a shortcut for sum that's in second stat. Actually, I think I have to go back to the home screen first, so let's do that. Second stat, and then in math, one of the options is sum, and then you tell it you want the sum of list 3. And so this is, it ought to be the same as what you did in the warm-up. I feel like I messed up a number somewhere because that's not quite the same as I remember it being. But anyway, it's in second math. So that is how you make the calculator do this process without the whole big table. It's a little bit of a table. It's only 3 columns instead of 5. And then, last but not least, not last, actually, then the p-value you could either get from table C, which I will put that in the canvas for you. We saw an interesting situation in the warm-up where table C gave us, it was off the chart, and so it was 0. So the warm-up value was off the chart, and we just said it was approximately 0. And it's not always going to be like that. So if it's not off the chart, it's a little more interesting, I guess. But you could also do on the calculator, you could do, there's a thing called, guess what? Chi-squared CDF. Oh, that sounds so familiar. It's just like TCDF or normal CDF. It's the same thing. And what we're going to do is put our chi-squared first and our 999, and then DF, which in this chapter, as you saw in the warm-up, it is the number of groups or categories minus 1. So number of groups minus 1. So chi-square CDF. And if I just use the answer that I just had, I get something really, 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 really small, like we saw in the warm-up. It's approximately 0. But if I did something more reasonable, like I'm just going to pick a number from a different example. Let's say I got a chi-squared of 11. Then I would get something a little bit more like you're expecting to see. So that's basically how you do it. You plug in your chi-square value here. It's always to the right. That's interesting. It's always a right-tailed test. And you'll see that on the chart also, the picture that you saw in the warm-up at the top of the chart. It always looks like a skewed right distribution, and the reason is that we squared everything. So we have 0 is the smallest possible chi-squared value would be if every single observed value was exactly the same as the expected. Very rare for that to happen, which is why this little gap is here. So usually you get pretty close to 0, and then over here you have the rare situations of what happens if you have way different than 0. These are the not rare, reasonably likely situations. And this little bit over here is the p-value, is the area in the right tail. And so that's what we're doing is we're calculating that little tiny bit over there, which might be 5% or more or less, depending on the situation. But it's always right tail because its chi-squared distribution is always skewed right. We'll talk some more about that next week also. And then last but not least, we talked about the conclusion. And the conclusion is the same as what we've been doing. Honestly, if P is less than alpha, then you reject. And if P is greater than or equal to alpha, then you don't reject. And this part I don't even have to tell you because you already know how to do it. So the example we saw in the warm-up, which I hope that you already did. I think I said that already, didn't I? Oh, yeah. So the example was since P was approximately 0, which is way less than 0.05, we reject the null. And remember, the null said that Harvard did not discriminate, that Harvard's admitted students have the same proportions of each race as their applicants. That same proportions idea is still really important, of each race as the applicant pool. We know the proportions for the applicants, and the proportions of admitted students were not the same. And so basically we have evidence that they discriminated specifically against Asian Americans, but we will come back to the specific part of the analysis next week. So I know I'm saying that a lot, that we're going to put things off till next week. That's because this is the first lesson of the chapter. I don't want to overwhelm you with too much stuff, but you kind of have an outline here of the 4-step test. We're not making it formal yet. They're going to ask you for pieces of this in the homework. So they might ask you to calculate chi-squared. They might ask you to write hypotheses. It won't make you do all 4 steps yet, but that's coming soon. And a lot more details than that are coming soon. So there you go. That is introduction to chi-square tests.